Hello and welcome to Wednesday's edition of Cracking the Cryptic, and today we're going to just be doing Killer Sudoku, normal plain old Killer Sudoku. And the reason I want to try this puzzle is it's come personally recommended by Christoph Seeliger. Now many of you will be familiar with Christoph's name. He's one of the world's best puzzle constructors and also a world-class solver. So when he tends to recommend puzzles to me, I sit up and listen. He says this one is hard but absolutely gorgeous. So yeah, we should be in for a treat. Anything else I want to mention before we kick off and try the puzzle? Not really. We've got obviously Mitchell Lee's video where he explains how to solve his odd even little Killer Sudoku, our competition puzzle. That is live for anyone who's a patron of the channel on Patreon. It's definitely worth checking out. The comments are they're so good. I mean, Mitchell is clearly very popular. I mean, people are asking for more videos by Mitchell, and many commenting on what a good teacher he is. So if you were struggling with that puzzle, definitely check out that video. It is fantastic. Now, let's go through the rules of today's puzzle. I should say, of course, this is by Quarterthru. Now, Quarterthru is not a name I recognise as a pseudonym, but I think Quarterthru is the same person as Jeremy Butler, in which case we have done many of Jeremy's puzzles on the channel before. So I think this is Jeremy Butler. The puzzle did appear on Logic Masters Germany. No rating yet. I think that's probably because it's very, very difficult. What are the rules? Well, as I say, normal Killer Sudoku rules. So we've got to fill each box with the numbers 1 to 9, each row, each column with the numbers 1 to 9, and in cages, those 4 squares, for example, would have to sum up to 22. And you can't repeat digits in a cage in Killer Sudoku. So in this 25 cage, we would have to make sure we were making 25 without repeating a digit. And that's all there is to it. So do have a go yourselves. Click on the link under the video to play. And with that, I get to play. Let's get cracking. It's ages since I've done just a standard Killer Sudoku on the channel, so this is a real treat for me. Look, we've got a 30 cage there, that's got to be 6, 7, 8 and 9. 30 cage there, that's got to be 6, 7, 8 and 9. Okay, now what next? We've got 31 in those 2 cages, 34 there, 24, 34, okay, 32 in the central box. Those 3 squares therefore sum up to 13, which is not a useful total, but if you're not used to it, Killer Sudoku, the reason I know these add up to 13, of course, is because the digits 1 to 9, which must appear in this 3x3 box, add up to 45. So 45 minus 14 minus 18 is 13, absolutely useless. Yeah, and the other thing that's becoming obvious to me as I study this grid is that all of the cages individually, certainly apart from these 230 cages, are not very helpful. I mean, this 15 cage has to be 6, 9 or 7, 8, which, I mean, 2, 3. There has to be a 1 in this 13 cage. I'm really scraping the barrel here, looking for logic. I'm going to put that in. The reason I know that, obviously, is that 2, 3, 4 and 5 added together add up to 14. Now, what can... now, hang on a second. Hang on a second. We might... Right, so we did a puzzle, in fact we did Christoph's puzzle the other day that used Pfister-Maffei's theorem. Well, it used Pfister-Maffei's theorem at a very sort of late stage of the solve, but one thing that is quite interesting to me is this ring in the grid is fully defined from a Killer Sudoku perspective. We can see, in fact, these squares add up to 109, 2 lots of 30 plus another lot of 49. So why does this matter? Well, I'm not sure that it does. In fact, I'm going to colour it in case it does. But Pfister-Maffei's theorem, and if you're not familiar with this, I'm about to drop your jaw. Pfister-Maffei's theorem tells us that this ring, whatever digits appear in this ring, appear exactly in those 16 cells in the grid. So whatever we put in the blue cells has to make a reappearance in the red cells. The 16 cells in the blue cells are the same as the 16 cells in the red cells. Now, I appreciate if you've never seen this before, that may strike you as surprising, as it certainly did to me when I first learned of it. It's named after Fistemafel, the genius constructor from Germany, who discovered it now, or certainly to my knowledge discovered it. And look, yeah, this is very, very, very interesting, because we are going to find look at this. We're going to have some sort of restriction that impacts the yellow squares, because if I know the blue squares add up to 109, and I'll explain the logic. If this looks important, I'll explain the logic for why this is the case. Just let me double check that this is how we're intended to start. If it is how we're intended to start, I love this puzzle already, because this, to start with Fistemafel's trick, I don't think I've ever seen that in a Sudoku before. Anyway, let's stop going on about that, and let's actually do some arithmetic. So what we've got here is 34 in those squares, plus 24, well that's 58, 73, 92, 103, 123. So the yellow squares add up to 123, but the blue squares add up to 109 because they're equal to the red ring. So the yellow squares add up to 14, which is a very small total. And the minimum I could make these squares individually would be, if I put 1 and 2 in each box, I'd have 4 lots of 3, which is 12. So there is very little latitude about how high these digits are. Let me just... So if these are all 1 and 2, is there a problem with that? Yes, there is a problem in this box. This box has a cage that equals 34. Now, if the whole box adds to 45, these three squares here, have got to add up to 11. But I can't make them add up to 11 if I can't use a 1 or a 2, because 3, 4 and 5 add up to 12. So this box I can't use 1 and 2 in. Oh, now this is very cunning. Look at this, what Quarterthru has done. This box, these cells here, these 6 cells, also add up to 34. And in fact, they form the same shape, but he's divided them into two cages rather than one cage. I wonder if that's to disguise this fact. But anyway, we've got the same principle here. These 3 squares have got to add up to 11. Therefore, you can't make those 2 squares 1 and 2. And if we know, therefore, that we had 2 degrees of freedom, because the minimum we could make these was 12, the maximum is 14, now I have to use 1 degree of freedom in box 1, 1 degree of freedom in box 9, and we end up here. And those add up now to 14, which is what they have to add up to because of the geometry and the topology of this puzzle. What a beginning. Now, hang on, I should tell you what I should do. Can I do this? I just want to... I know many of you are familiar with Fistemafel's theorem, but if you're watching this video and you're wondering what magic I am claiming to have performed there, can I do that? Yes, I can. Right, I just duplicated the tab. So, let me try and explain what I did there. Now, I am claiming that the red cells and the blue cells have to be exactly equal. How do we prove this very straightforwardly? Now, the way I like to prove this, I did this in a video the other day, this is the simplest way I've found of understanding it. If we look at, add the green squares in. Right, so what I want to do first is to study row 3, row 7, column 3 and column 7. Now, if I asked somebody to tell me, what would be the contents of those 2 rows and those 2 columns, how could we describe those things? Well, hopefully it's pretty obvious from this that because this would be a complete row, that would contain the digits 1 to 9. This would be a complete row, that contains the digits 1 to 9. This complete column has the digits 1 to 9, and this complete column has the digits 1 to 9. So we could describe row 3, row 7, column 3 and column 7 as 4 lots of the digits 1 to 9 minus these 4 corner squares, which appear in both, they sort of duplicated in that arithmetical sum. So these rows are exactly equal to 4 sets of the digits 1 to 9 minus whatever we put in those 4 squares. Now, if I was to ask the question a different way and ask what these yellow squares, how would we describe those yellow squares? Well, you can see it's almost 4 complete boxes of the Sudoku. So it's almost 4 complete sets of the digits 1 to 9. And it's equal to the 4 sets of the digits 1 to 9 minus those 4 squares. So we know that this set of digits here is exactly identical to what I described about rows 3, row 7, column 3 and column 7. Therefore, I can make them equal to each other. So I know that the blue squares plus the green squares is exactly equal to the green squares plus the red ring. That's what we've just shown. Well, you'll notice that on both sides of that equation are the green squares. So I can just deduct those out of both sides of the equation and prove that the blue squares equal the red squares, QED. Now, when I first saw this, I have to say I thought that somebody had, just opened up a mystery of the universe, because it's quite extraordinary. Of course, this applies to any Sudoku, not just a killer Sudoku. Any Sudoku this is true for. So let's go back to what we were just looking at. Here we go. And try and... So hopefully you're now convinced that what I've put into the grid is correct. And now we have to try and solve the puzzle. Use it. We've still got no digits, of course. But we have got something very interesting. Right, so the first thing that jumps out at me here is that the ones in these 4 boxes are locked into the same subset of rows and columns. So I know that if there's a 1 here, this is sort of, I don't know, how many skyscrapers would it be? 4 different skyscrapers. So if this is a 1, this will be a 1. If this is a 1, this will be a 1. Now that means that the 1 in each of these boxes has got to go into the squares I've just highlighted. So in fact, that one we'd almost got to anyway. But we can remove the 1 from this square. It must be in one of these 3 positions. In this box, these 3 squares sum up to 11, so they have to be 2, 4 and 5 because they can't use 1 and 3. The same must be true down here, of course. Now, sorry, I'm sure that there is a 1-2 pair here in a 20 cage. So those 2 squares have to add up to 17. They've got to be 8 and 9. Oh, and of course, right, look, in this 2x2, this 2x2 has to add up to 30 because the whole cage adds up to 34, and we've removed 4 by putting the 1 and 3 into these cells. So if those squares have got to be 6, 7, 8 and 9, and there's an 8, 9 pair down here, we can get more of a restriction. So now look, there must be an 8 and a 9 in 2 of these 3 squares by Sudoku because of these pairs. Same thing is true down here. So this is a 6, 7, 8 and 9. In fact, that's interesting. So this domino adds to 15. As the whole 2x2 adds to 30, this domino also adds to 15. And okay, here's something quite interesting. So, or at least I think it's quite interesting. This set of digits is the set of digits 6, 7, 8, 9. This is the set of digits 6, 7, 8, 9. Now we know from Pfister-Maffel's theorem that these two sets of digits have to reappear in our red ring, and you can see they have already done that in the 30 cages. So these squares actually are exactly equivalent, if you like, which means that the other 2x2s in box 3 and box 7 are whatever digits are in these two 2x2s are exactly equal to whatever we put in these 8 cells here. So actually I think I'm going to change the highlighting now. I'm going to make these red. Is that a sensible idea? Maybe. Let me go with it and see. And those blue. And the reason for that is that I'm trying to make sure now that in the blue, I've got to make sure this blue and this blue is equal to this blue and this blue somehow. Gorgeous, gorgeous. Now, look at this blue and this blue. In both of these cases, there is a 2 locked outside the blue 2x2 region. Now that means that in our blue Pfister-Maffel ring in the centre, you can't put a 2 in it, because it's not possible to put a 2 in any of those cells. So this square is not a 2, and this square is not a 2. And I've still got no digits in the grid. But that feels important. The fact I can't put a 2 in the blue cells. Yes, got it. Right, now look. This is a 22 cage. So I can't put a 2 in it, given it's already got a 1 in it. This is gorgeous. Now, if I can't put a 2 in this cage, and I can't put a 2 in here because of Pfister-Maffel's theorem, where does the 2 go in box 2? It must be in this domino. Why does that matter? Well, it tells me that's a 1. Now that might... Does that get everything? It does. That gets me all of these 8 digits around the edge of the grid. How... That is stunning, stunning Sudoku setting. 2. Where does 2 go in box 9? This 2 is forcing it here. That gives me a 4-5 pair. So look now at this box. If this is a 4-5 pair, I can't put the 4 and the 5 in the 11 cage because they don't add up to 11. These are the things you learn on cracking the cryptic. So where does so one of the 4s and 5s must go in there, which forms a pair here, which means this is a 2, which we could have got from that 2. So a duplication of logic, but it's still good. So 2 now, look, there must be a 2 in the 13 cage. In fact, if we look down column 2 of the grid, I've not placed 3, 4 and 5 yet, so those 3 squares have got to be 3, 4 and 5. 1, 2, so... Oh no, that's not... Okay, stuck a bit there. 2 has got to make an appearance in the 16 cage just by Sudoku over on this side of the grid. Now this 3 therefore is important, because where does the 3 go in box 6? If the 3 goes in the 16 cage, there would be a 1, 2, 3 in it, they add up to 6. The other digit would have to be a 10. That's not possible. We can't put 10 into a cell. So the 3 must go in there, therefore the 3 must go in one of these 2 cells. 24. What's 4, 5, 6 and 7 add up to? Too many. Too many. So let's have a look at this box. Is it possible this box doesn't contain a 3? Well, if it doesn't contain a 3, the minimum I could put into these squares would be 4, 5, 6 and 7, which add up to 22. 22 plus 1 plus 2 is 25. So there is a 3 in one of these cells, and it can only go there because of the Sudoku restrictions. So now there's a 3 in one of these two cells. This square has got to be 6, 7, or 8, 6, 7, 8, or 9 by Sudoku. Look, because we've got a 4, 5 pair in this column, and obviously 1, 2, 3 placed. 3. 3 can't go here. Oh, where does 3 go in box 7? I can't put 3 in the 11 cage, because if I do, it has to accompany an 8, and I know that 8 is not in the 11 cage, so I think the 3 can only go there. Which means there is a 3 in the 15 cage, which means that... no, they could still... I was wondering whether I could force a 2 out of the 15 cage, but I can put a 2 in there if there is a 9 in there as well. So that's no use. So let's go back to checking we've got the digits mapping here. So 8, 9 here, actually, look, that can't be 8 or 9. So this is a 6 or a 7. Ah, yeah, okay, so there's a 6 or a 7 in the 11 cage along with a 4 or a 5. So there's a 6 or a 7 in the 13 cage. So there can't be a 5 in the 13 cage, because given we know there's a 6 or a 7 in there, if we put 5 in there as well, the minimum we'd have is 6 plus 5, which is 11, and the other two digits would have to add up to 2, and I can't put repeated ones in that cage, so that is not... There's definitely a 5 in one of those cells. Now, what can we do next, if anything? I feel like this cage is a bit restricted, given I've got a 3 in it. And I've got to put a 4 or a 5 in it. So 3 plus 5 would equal 8. So that would mean the other two digits had to add to 16. So one thing we can say with certainty is there is definitely a 9 in this 24 cage. So there's a 3 and a 9, a 4 or a 5, and a 7 or an 8. 20. I'm just wondering if we put the 9 in here, 12, 34. No, this is a good deduction. We're going to be able to get this square. We know there's a 9 in the 24 cage. We know it's not here. Can it be in this box? Now the answer's no. Because if the 9 is here, we can do geometry on this box. This adds to 12. This adds to 12. That adds to 22. This adds to 12. So these 6 cells together add to 34. The whole box adds to 45, which means these 3 squares would have to add up to 11. Now the problem is this square has to be quite a big number. And you can see whichever one of these big numbers I choose, this is impossible. Even if I choose 6 here, I've got to make those two add up to 5. It's not possible. One of them's a 2, the other one would be a 3. It will clash. Anything bigger, and I'm going to have to put a 1 in here, which will clash, obviously, with this one there. So this is not 9. And where do we put the 9 in this box then? It's got to go there. So neither of these are a 9. Which means this is a 9. Now this 9, does that tell us anything new? I feel like... one thing it tells us is now I can't put a 9 in the 15 cage. There can't be a 2 in the 15 cage. So the 2 must go in one of those cells. Oh, surely this 9 must be more important. That can't be a 9. Ah, yeah, hang on, look. If we look at this row, I've actually got quite a lot of info about it. I know 6 of the digits, roughly. So this pair has to include an 8 and has to be picked from the digits 6, 7 and 8. Ah, now this is interesting as well, actually. This is very interesting because now, what is this square? And in particular, can this square be a 9? And I think the answer is no, because if I pick the minimum for those 3 squares, I would have 6, 7 and 4. Well, 6, 7 and 4 add to 17, so the maximum this square can be is an 8. And the minimum it can be, if this is 5, 8 and 7, 20. Oh, we can't repeat the 5, so the minimum this can be is a 6. So this is a 6, oh, this is a 6, 7 or 8. So there's a 6, 7, 8 triple in this box, which means 6, 7 and 8 add to 21, so this is a 4. That's a 5. Okay, is that helpful? Yes, it is. It is helpful. There's a 4 in one of those 2 squares and a 4 here. So 4 has got to be in there. In fact, that's a quadruple as well, so that's got to be a 5. I could have just written that in if I'd looked at it. So 5 now makes an appearance in one of those squares. As this is a quadruple on 6, 7, 8 and 9, we know the 9 must be in one of these 3 squares, and we can't repeat a digit in a cage, so that's not 9. We know 9 isn't in those 2 squares either. Ah, I feel like I'm missing something here. 4, 5... What is it? Is it something to do with Fistenfell again? Because now I've got the 4 maps here. Look, 6, 7 and 8. There's an 8 here, so 6, 7 will appear in one of those squares. There's obviously going to have to be a 6 or a 7 up here as well. I don't know, 10. Ah, yeah, here we go. Here we go. We've already got cells summing to 10 in this 24 cage, so the other 2 cells have got to sum to 14 without using 5. So this is a 4, 6, 8 triple, which means this is not 6 or 8. This must be a 7 or a 9 to complete the box. This can't be a 7. Oh. So these 3 squares have to be 3, 6 and 8. Oh, where's the 3 gone? Come back. And given we know one of these is a 3, is 3, 6 possible? No, because 3 and 6 add to 9, plus 9 is 18. I can't get to 24, so this is a 3, 8 pair, which means that's a 6. So we don't have any more 6s in the box, so 6 must move down here. Oh, this is huge now. 7, 8 pair here, so this has to be a 6. And now 6 in this box is forced into the left-hand side. So this is a 1, 2, 6 triple. 1, 2 and 6 add to 9. This square is a 4 to make up to 13. 3 and 8 add to 11, plus 9 is 20. This is a 4 to make 24. And I think all of a sudden it feels like the puzzle is starting to give up its secrets. Oh no, don't let me say that and then it stop giving up its secrets. Please. Oh, can we do arithmetic on this box now? We've got 22. 22 plus 17 is 39. Ah, yes we can. This domino has to add up to 6 in order to get the box to add up to 45. 2, 4 here, so this square becomes a 4. 6, 8 here means that square's a 9. 8. Actually, the 6 does the 7 and the 6 as well. So this is 2, 4. So we can write in the value of this square. This must be a 5 by Sudoku. These squares are 1, 7 and 9 by Sudoku. This is a 4, 7 pair. It's a complete box 7. And now we should be able to justify Fist-Maffel's ring. Look, we've got a 4, 9, 6, 4. So 4, 9. There's a 6 up here. Another 4 here. That's perfect. 4, 6, 7, 8 being the remainders. Yeah, so I'm not sure whether I have already highlighted 2 4s or not. I'm going crazy. 4, 9, 3, 8. 4, 8, 3, 9. And 4, 7, 8, 6. 4, 7, 8, 6. Yes, it is correct. I mean, it should be correct. So I'm not really surprised by that, but it's nice to know. Now, I've done this one. I haven't done this 15, and I've not done this 16. I know the 3. So I've got 2 squares here that add up to 3. The other 2 squares add up to 13 without using 6, 7. And including a 4. Good grief. So there is a 4 in this 16 cage, so the 16 cage is now forced. It must be 1, 2, 4 and 9. And this one is not... in fact, that one is 9 by Sudoku. There's a 1, 2, 4 in the column. So 9 goes here. This 9 tells us that this 15 domino here is not 6, 9. So this is 7, 8, which means this is not 7, 8. 6, 9 points at this square. That's a 7, a 9. That's not 9, therefore. This box needs a 3 and a 5 to complete it. This 6 sees these 2 squares and completes the 6 and the 8. So I think, other than the middle, we're just left with this 15 cage. I might be wrong about that, but... So this 15 cage at the moment includes 4, a 1 and a 3, so that's 4. So it needs 2 more adding up to 11. And it can't, and it's got to be 5 and 6, doesn't it? Because it can't be 2, 9, it can't be 3, 8, and it can't be 4, 7. So this is known. This is 1, 3, 5, and 6, which means these 2 squares are, like these ones, are 2 and 4. 2, 4 sees this 11 cage, so we get some more progress here. 7, 4, 7, 8, 8, 9, 9, 6. That square is a naked single. It's so... I don't know if the symmetry is deliberate, but I'm sensing it here. We can remove the 1s and the 3s. This can't be a 6 because of the 6 up here. And I can get rid of the 1s and 2s here to tidy up pencil marks. And what are we left with? How do I finish this off? Oh, I don't know, actually. This has suddenly become confusing. 9 has to be in one of those 2 cells. Oh, look, there's a 3, 5 and a 7, 8 pair in row 5. 2, 4 pair in column 5. If this was a 9, what do we got here? We've got 32. These add up to 13. If this was a 9, these would have to be 1 and 3. That looks... Well, it doesn't look immediately impossible, actually. If this was 9, you'd have to put... You couldn't use 1, 4. This would have to be 2, 3. Ah, that also looks possible. Okay. So we're going to have to try and work out how to disambiguate this central box somehow. I'm going to look at row 5 because I've got this funny these funny pairs in it. I need 1, 2, 4, 6 and 9 into these squares. 1, 2, 4, 6 and 9. Now, can we rule any of these out? We can rule 9 out from that one, 6 out from this one, 2, 4 pair in this column. So this square has suddenly become much more restricted. And this one is in an 18. Oh, yeah, this one's in an 18 cage. In fact, this has to be a 6. Look at that. Because if we put a 1 or a 2 into this square, we have to put a 9 below it, because 1 would give 17, which would need 9. 2 would give 16, which needs 7, 9. So 1 and 2 are not possible. But 4 is also impossible, because now I need 14 here. 6, 8, 5, 9, both impossible. So this has to be 6. That's not 6. Oh, in fact, that's, look, this, we get a 6 over here. Maybe this is what I was missing. That's not, oh, that's not 6. 6 appears down here. These add up to 12 without using 3, 9. So these are either 4, 8 or 5, 7. But if it's 4, 8, there's a 4 in this column already, so the 4 would have to go here, the 8 would go here. And if it's 5, 7, that has to be 5, that has to be 7 because of this 5. So we're... Oh no! We're nearly there, but not quite. 13. Right, but we can do... Yeah, look at the 2, 4 pairs. This is a nice trick. A nice trick here. We can't put stuff in these 2, 4 pairs that plonks a 2 in the central diagonal here, because it's got to accompany a 1 or a 9, and it's got to equal 13. So if there's a 2 here, how would we do that? It's not possible, because if this is 9, you have to repeat the 2. If this is 1, you've got to put 11 into this square. Neither of those works. Now, why is this important? Well, let's get this the right way round. Yeah, if this is a 2, that would be a 4, that would be a 2. Now, where do I put the 2 in the central box? It's got to go on the diagonal, where I mustn't put it. So we can use that to say this is 4, this is 2, this is 4, this is 2. Now, that plonks the 2... Whoa, keep double-clicking. Or right-clicking. So that plonks the 2 over onto this side. We know the 2 is not on the diagonal. So the 2 is now in the 14 cage. So there's no 1 in the 14 cage. There's no 4 in the 14 cage because of this 4. But now, look, where does 4 go in the middle box? We can do Sudoku. It's forced to be here. Now that's huge, because that makes that one an 8, which gives us an 8, 7 here. In fact, it gives us 8 7s there as well. And 8 7s here. And now 7 must be in one of those 2 squares. And this, I feel, could be the breakthrough. We've now got a 1, 2 pair in row 6. So, look, so we haven't placed 3s and 5s yet. This square has to be a 3 or a 5. There's a 5 above it. This is a 3. That fixes the 3, 1 at the bottom. That's not 1 anymore, therefore. These have to add up to 10, because we know these 3 add up to 13. So if these add up to 10, this has to be a 1 or a 9, then it can't be a 9. And that, oh no, oopsie. That's a 1, that's a 9, that's a 7, that's a 9, that's a 1, that's got to be a 2, these have got to be 5 and 7, and it works. 7, 5, 8, 3, 3, 5, 2, 1, 4, 1, 2, 5, 3, and that is as good, yes, as good a killer Sudoku as you will ever see in your lives. Absolutely stunning puzzle, Quarterthru. Absolutely stunning. I hope you enjoyed that. I'm watch me wade my way through it. But the start of that puzzle is a joy, absolute joy. And yeah, well, let us know in the comments what you thought, and we'll be back later on with another edition of Cracking the Cryptic.